Hello viewers, welcome to our series on binomial theorem. In the previous two lessons, we introduced you to binomial theorem, Pascal's triangle where we saw certain patterns, and then the proof of binomial theorem which we had done using principle of mathematical induction. In today's lesson, we will be dealing with certain problems where we will use the general term of expansion of a binomial using binomial theorem. Let us just recall what binomial theorem is and how does it help to know the general term of a binomial expansion. Remember, we are dealing with binomial theorem for positive integral index. So, we are looking at the expansion of the binomial a plus b, and the power, that is a plus b raised to the power n, is always a positive integer. So, with that condition, we know that a plus b whole to the power n to be same as nc0 a to the power n plus nc1 a to the power n minus 1 times b plus nc2 a to the power n minus 2 times b squared plus so on up to NCR a to the power n minus r br, and this sum ends with NCN b to the power n, where of course NCR, which is at times also referred as the binomial coefficient, is equal to nothing but n factorial by factorial of n minus r times r factorial. Once we know that this is the expansion, there were certain observations that we had made, and it is helpful to recall those observations. The very first was that when you expand a plus b to the power n, the total number of terms that you get is always, yes, 1 more than the index. So, a plus b to the power n will always have n plus 1 terms in the expansion. Now, what do we mean by general term of a binomial expansion? When I am looking at the general term in this expansion, it is nothing but the r plus 1th term, and that has the value same as NCR a to the power n minus r into b to the power r. R plus 1th term will have the binomial coefficient as NCR, and we are looking at the expansion written where we are decreasing the powers of a and increasing powers of b as we expand. And with that thought in mind, we have enough to work with for our few questions that have been selected for this lesson. So, let us start with the very first. Show that the middle term in the expansion of 1 plus x whole to the power 2n is, and the value of the expression is 1 into 3 into 5 going up to 2n minus 1. So, it is a product of such numbers which you can definitely identify to be odd numbers, right, divided by n factorial into 2 to the power n into x to the power n. So, I have to show that the middle term in the expansion of 1 plus x whole to the power 2n. Now, middle term is nothing but depends on position. So, position of the middle term needs to be decided. In this case, the expansion of 1 plus x to the power 2n will result in how many terms? 2n plus 1. We just recalled that for you. So, out of 2n plus 1, which is the middlemost term? What is the position of the middlemost term? So, if I have 2n plus 1, which is nothing but odd, irrespective of what n is, 2n plus 1 is an odd number. So, out of those odd values, odd many figures, expansion terms, what would be the position of the middlemost term? Exactly, n plus 1th term. So, in other words, you have been asked to find the value of t n plus 1. So, are we ready to write that? We have of course the TR plus 1, which is 2NCR, 1 to the power 2n minus r into x to the power r. And in this case, r happens to be n, because I am looking at n plus 1th term. So, Tn plus 1 takes the value 2n Cn x to the power n. Now, also another thing that you can appreciate about this question is that this is being done very specifically for a binomial of the form 1 plus x. So, I have not much to work with, but only the 2n Cn. Now, if you rewrite 2n Cn x to the power n using the factorial notation, it turns out to be factorial of 2n divided by n factorial into n factorial. Since I need to simplify, expand, rewrite this, what I can do is I can expand 2n factorial. Now, 2n factorial on expansion will become something like 2n times 2n minus 1 times 2n minus 2, going right up to 4 into 3 into 2 into 1. The rest of the expression remains as it is, that is divided by n factorial times n factorial into x to the power n. Now, the idea is that you have to get a very specific answer. So, it will not hurt to take a good look at what you want. So, if you observe what you want, then in that case the numerator has all odd factors only. In the product that we have got after expanding 2n factorial, which would mean that when I expand 2n factorial, I have 2n factors. Out of these 2n factors, n factors are even and n factors are odd numbers. Do you agree? So, which of them are even? 2n, 2n minus 2, 2n minus 4, going right up to 4 into 2, and all others, that is 2n minus 1 times 2n minus 3 up to 3 into 1, they are all odd factors. So, what we are going to now do is club these odd and even together, and in this case what will happen is, therefore, I have now segregated the even factors and odd factors. Now, intuitively you can possibly react and say, well, out of 2n, 2n minus 2, 2n minus 4 going up to 4 into 2, 2 is common from each term and there are n such factors. So, if I take 2 common out of each of these factors, in other words, I am writing 2 into 2 into 2 how many times? N times. And what am I left with? I am left with n into n minus 1 into n minus 2 right up to 1. And so, do you see a pattern being formed here? 2 multiplied with itself n number of times is going to be nothing but 2 to the power n. And what is n into n minus 1, n minus 2? Continued product going right up to 1, which is exactly what n factorial is. So, do you see you are coming very close to the answer that we are aiming at. I end up with 2 to the power n times n factorial into all the odd factors that we had segregated into x to the power n divided by n factorial into n factorial. So, that n factorial gets cancelled and I have the final answer as the middle term in the expansion of 1 plus x whole to the power 2n is 2 to the power n times 2n minus 1, 2n minus 3 up to 3 into 1 divided by n factorial, all of this multiplied with x to the power n. So, this question was more on simplification, starting with the idea of the position of the middle term to the simplification of the factorials to a very, very special expression. Let us see what the next question has in store for us. Find the coefficient of x to the power minus 2 in the expansion of 2x to the power 5 minus 1 by x squared whole to the power 8. X is not 0, so that the expression is defined. So, here we are not talking about find the fourth term or the middle term, but find the coefficient. Coefficient would be the numerical coefficient, numerical number which you will end up with as identifying as a multiple of x to the power minus 2 in this expansion. So, definitely we are not going to expand this entire expansion and then identify. We are again going to make use of the general term. We have to identify that value of r so that the term that we end up with contains x to the power minus 2. So, how do we start? T r plus 1. So, in this case, I have T r plus 1 specifically written with the n as 8, a as 2 times x to the power 5, b as negative 1 by x square. R we do not know. So, we hold on to that, and therefore, T r plus 1 becomes, on rearranging, that is on combining the powers of x and segregating the constant, starts looking like 8 C r 2 to the power 8 minus r, x to the power 40 minus 5 r, negative 1 to the power r, x to the power minus 2 r. So, if I combine powers of x, I get the powers of x combined to 40 minus 7 r, and all the constant coefficients remain as they are. Now, the problem said find the coefficient of x to the power minus 2. So, we need to find that r for which the power of x is negative 2. So, what would one do? Of course, equate that 40 minus 7 r to negative 2 and then solve for r from here. So, I am sure you are ready now to say r is 6. So, which term will give me x to the power minus 2? Not the 6th term, but the 7th term. Remember, we are talking about T r plus 1, and therefore, if I substitute r is equal to 6, I get the coefficient of x to the power minus 2 as negative 1 to the power 6, 8 C 6, 2 to the power 2, because 8 minus 6 is 2. And therefore, if you just calculate a little, you end up with your final answer as 112. So, 112 is the coefficient of x to the power negative 2 in the expansion of the given binomial raised to the power 8. Are we good with that? So, another problem will expose you to some more idea. Find the term independent of x in the expansion of x square minus 1 by x whole to the power 12. So, what is term independent of x? If I call it absolute term, are they one and the same? Term independent of x, as the literal meaning would be that there is no x in that term. That means power of x reduces to 0 in that particular term when I expand this. That is exactly what you have to do. So, in other words, you have to find the coefficient of x to the power 0. Absolutely same as the previous, in the sense there we were finding that r for which you would get power of x as negative 2. Now, we will aim at finding r such that x is to the power 0. So, we are looking at the same start with general term. T r plus 1 is NCR, a to the power n minus r, b to the power r. For the given expansion, n is 12, a is x squared, b is negative 1 by x. We do not know for what r we will get the independent term. So, if we write the T r plus 1, it is 12 C r x squared to the power 12 minus r, negative 1 by x to the power r. So, I am sure you are now ready to say, oh yes, I can do it. I have to just collect the coefficients, constant now terms separate and powers of x together. So, I end up with 12 C r negative 1 to the power r. Do not neglect negative 1 to the power r. It depends on what r would be. If r is odd, you will have a negative value. If r is positive, negative 1 to the power even number would be positive. So, in this case, I am looking at independent term, that means I am going to put 24 minus 3 r to be 0. That gives us r to be same as 8. So, the term independent of x position wise will be the 9th term, but we have to get the value of it, and that will be nothing but 12C8 into negative 1 raised to power 8. So, I have an even power, and therefore, the term would reduce down to be a positive term. In numerical value, it is same as 495. Sometimes certain authors, certain textbooks also call the term independent of x as the absolute term. So, you may be asked to find absolute term, but typically this is exactly what you would be doing. What does our next question say? Find numerically the greatest term in the expansion of 1 plus 4x to the power 5 when x is 3 by 4. Now, this is a little different than the previous two problems that we have discussed. We have to find the term which takes the largest value, and we are looking at a specific stage or specific condition applied, that is when x is 3 by 4. So, if I assume that TR plus 1 is the greatest term in this expansion, then that would mean that TR plus 1, which takes the value 5CR 4x whole to the power r, this will always be greater than equal to TR, which is nothing but 5CR minus 1 4x to the power r minus 1. So, I get some start by comparing TR plus 1 and TR. So, if TR plus 1 is to be greater than equal to TR, it will mean that 5CR 4x whole to the power r must be greater than equal to 5CR minus 1 4x raised to power r minus 1. So, from here I have to figure out what this r possibly can be. If I simplify this, considering that if I divide and I have my expression reduced down, I will have a condition or a value from where I can deduce what term I am going to be getting. So, rewriting 5CR and a 5CR minus 1 in terms of factorial, simplifying between 4 to the power r and 4 to the power r minus 1 in the denominator, combining powers of 4, I get only a 4 left, and x to the power r minus r minus 1 will give me a power of x as 1. So, the condition that I get is that TR plus 1 is the greatest term if 6 minus r upon r into 4 times x, but x was given to be 3 by 4. So, when x is 3 by 4, this inequality will let me know what condition I have on r. So, if I just rearrange, simplify, I get 18 minus 3r must be greater than equal to r. Also remember, r is related to the position. So, r is always going to be a positive integer, right. So, in this case what do I get? That r must be less than equal to 18 by 4, which is same as saying that r must be less than equal to 1 by 2, 4.5. But r was a positive integer. So, if r is a positive integer, therefore, for the term to be the greatest, that means as long as r is less than equal to 4.5, the terms goes on increasing. But r is a positive integer, therefore, the greatest term would be arrived when r is equal to 4, and therefore, the term that we are looking for is the fifth term. So, the greatest term numerically will be the fifth term in that expansion, and what will be its required value? If I replace r by 4, I get the greatest value, which is nothing but 5C4 4x to the power 4, which on simplification turns out to be 405. So, it is a little different than our previous questions, but give it another try and I am sure you will be very, very comfortable with it. In the next question, you are asked to prove that 9 to the power n plus 1 minus 8n minus 9 is divisible by 64 whenever n is a positive integer. Now, this sounds like a very much a mathematical induction problem, but can we do this with binomial theorem? Surely, if I start with writing 9 to the power n plus 1 as 1 plus 8 to the power n plus 1, then if I use the expansion with, of course, now a being replaced by 1, expansion would be much simpler. So, if I rewrite this expansion with the increasing powers of 8, it will look like n plus 1 C0 plus n plus 1 C1 into 8 plus n plus 1 C2 8 squared and so on up to n plus 1 Cn plus 1 8 to the power n plus 1. This gets rewritten using the value of n plus 1 C0 as 1, n plus 1 C1 is n plus 1 times 8 and so on. Now, you can see that you are getting that 8n plus 9 as well. So, if I shift this 8n plus 9 to the left hand side, I would get 9 to the power n plus 1 minus 8n minus 9 to be equal to n plus 1 C2 8 squared plus n plus 1 C2 8 cube, so on up to n plus 1 Cn plus 1 8 to the power n plus 1. From each of these terms on the right hand side, 8 squared is common. So, if I take that out, I am left with that entire expression on the right hand side to be a multiple of 64. And isn't that what we wanted? We wanted to prove that 9 to the power n plus 1 minus 8n minus 9 is a multiple of 64, hence divisible by 64. So, binomial theorem definitely comes in handy even in those situations. How about this one? Prove that summation of 4 to the power r NCR is same as 5 to the power n when summation index r is running from 0 to n. Now, summation and expansions are basically one and the same. So, if I write this summation symbol replaced as expanded form, it looks like NC0 4 to the power 0 plus NC1 4 to the power 1, NC2 4 to the power 2 right up to NCn 4 to the power n. So, isn't that same as what we have seen earlier when in place of A you have a 1, in place of B you have a 4. So, if I rewrite using that idea, the entire of the right hand side is nothing but 1 plus 4 whole to the power n, which is nothing but 5 to the power n. Now, this kind of a question tests your understanding of binomial theorem, is a very short answer question, can be tested as a 1 marker. So, I hope you are now ready to face any of these challenges, but we still have a few more for you coming up in our next lesson. So, stay tuned and stay learning. All the best till then.